Okay. Live. It's alive. It's alive. Okay. A little higher today. Okay. Looks like people are coming in. Almost halfway there. Hello, everybody. So, before we begin, let's talk about Monday. It's Labor Day. That means all good, God-fearing working Americans get the day off. And I think we do too. I'm 90% sure we get Labor Day off. But John Carroll's fall 2020 calendar is hard to locate. So, the moral of the story is don't redesign your web page at apparently the lowest possible bidder. Because, wow, do I have no idea where to find anything on that new web page. So yeah, I do believe we have Monday off for Labor Day. If we don't, then I guess you get the day off on account of me being an idiot and not knowing that we didn't. Let's, just as a little exercise, try to find the John Carroll Fall 2020 calendar. Wow. That's JCU's fall plan. That's definitely not it. And then we have what looks legit but links to a PDF. So not great. I'll probably end up clicking that. And then two legit looking ones that aren't legit. So I pulled this up so we can practice our cybersecurity skills a little. Let me zoom in on these bad boys. First one, jcu.edu, looks good. Second one, webmedia.jcu.edu, still looks good. You can tell it's from John Carroll because the last thing before the domain name before the .edu is still jcu.edu. Is JCU, right? So the last thing before the .edu is always what you want to look at, the last thing before the domain. But it's a PDF, and you don't really want to click random PDFs from the internet unless you trust them. I don't super duper trust the John Carroll website. But then further down we have jcu.smartcatalogiq.com. Not John Carroll. That is a different website that wants some clicks, and they probably got quite a few from people who don't realize that that's actually not John Carroll. But the correct one to click, probably this PDF, and we're going to look to fall here, and it says Labor Day, no classes, so I believe we don't have class. Unfortunately, if I go back to this first one, the actual first result on Google, then I'm going to see this JCU 2020 fall plan here, and if you click through these messages, I don't remember where it's at, but eventually you're going to find their planned calendar, which says that we're going to cancel the Labor Day being off thing. So I don't know where that's at, but it's somewhere around here. I definitely clicked through previously. Oh, here we go. We'll start instruction at the currently scheduled date, Monday, August 31st, but we will forego our two scheduled holidays, Labor Day. So, do you get Monday off or not? I don't know. I don't know. But I'm giving it you off because I couldn't figure it out. Any questions on whether or not Labor Day is a day off? Okay. Let's go on to today's slideshow. We're going to start doing networking stuff. We are going to learn the different networking layers over the next week or two before we begin using them. And we're going to start with the physical layer. We're going to get physical today. All right. The physical layer. This is the beeps and boops and electricity and bobs that pass your information over the series of tubes of the internet. Bring that from place to place. So not a lot to do for a software developer at this level. This is mostly for the hardware developers and the electrical engineers to work with. Now, back in the old days, before the internet even existed, the world was still connected, and the first way that the world became interconnected was by copper. Copper cables laid across the Atlantic Ocean were revolutionary. Before that, the only way to send a message across the ocean from the United States to England, where the first copper cable was run, was to take a ship. The journey took about a month or so, and the ship could sink, and your message would be lost forever. And if they wanted to send a reply, then it would take another month to get the reply. The first copper cable was very difficult to run. There were a lot of false starts. The first one they put down broke in something like 3 weeks, and then it took about a decade for them to try again. And that one had some troubles and took a couple of years for them to try again, and then finally they got it down and realized it was possible. But you have to marvel at what kind of achievement it is to lay a cable all the way across the ocean. Then after that one, they laid a whole lot more, and eventually you get to a map like the one pictured here from the Eastern Telegraph Company's system with all the different links around the world, linking a bunch of different countries in the world together by copper wire so they can send telegraphs to each other. Copper wire is electrical cable. The signals are transmitted by electricity. Electricity has really limited bandwidth. The early days of the technology required very large, expensive cabling, big, thick pieces of copper, very heavy, very difficult to put on a ship. They had to use multiple large military vessels to lay the cabling, taking a few trips. Right? These are big, heavy cables. And the latency, the delay was huge. It would take you, on the first transatlantic cable, 2 minutes to send a single letter or number. So a single character took 2 minutes to transfer. So to type out a whole message by telegram on the first telegram would take you literally hours, and then you would have to still get confirmation that they got it, and then the reply would take hours. But this was still an improvement of many, many magnitudes, because they didn't have to sail across the ocean to message each other anymore. And again, that first cable linking the two English-speaking nations of the world, America and the United Kingdom, which had just killed each other 100 years ago, and were now friendly enough to sponsor the first cable connecting the two of them. So a really nice lesson about the whole world coming together. But modern communication is based on light, which is funny because it's also one of the oldest forms of communication. Light is obviously the fastest thing in the universe. You can't travel faster than the speed of light. And pulses of light to communicate information are nothing new. Smoke signals are a form of communicating by light. So are flares and warning piles, blinking your flashlight at other people, lighting the fires of Gondor. All of those are examples of communicating with lights. So warning pyres and guard towers are nothing new. And ancient people used networks of guard towers with light signals to communicate over vast distances. So on a wall, you would have guard towers staffed by people who had a torch or something of some kind. And if they saw invaders, they would wave their torch or light their fire in a particular manner, and that message could propagate down many, many miles in a matter of minutes instead of in a matter of however long it takes people or horses to get that far, which is quite far. So light is nothing new. What is new and what comes in the mid-1900s is the discovery of the fiber optic cable. Everybody's probably seen fiber optic cable before. You've probably played with it as a child's toy. You have those little light-up things with the fiber optic cable. You've probably never given it too much thought, but it's actually a magical material. The first transoceanic cable is laid in 1988, so not that long ago. Now it's called TAT-8, and that again connects the US and the UK, now France, because France's economy is good and they're more friendly at that point. And this cable is replacing, at that time, phone cables, so it's designed to handle phone calls. I have a bandwidth equivalent there of 20 megabits per second, but it was actually designed to carry a certain number of phone calls, not internet bandwidth, because in 1988 there wasn't much internet to speak of. So there were already many transoceanic cables at that time made of copper carrying phone signals, but this was considered a revolution because it could carry something like 1,000 or 2,000 phone calls at once, which was incredible at the time. And that had just two little fiber pairs. Fibers, as you can see a little further down, they're only a few millimeters thick. They're a little thicker than they are in that picture. The transoceanic ones are maybe like, I don't know, 3 centimeters or something thick. You get a few pairs in a cable usually. That first cable, TAT8, had just two fiber pairs. And recently Google laid the faster cable. I don't remember what it's an acronym for, but that's what they call it. It connects Japan, China, and the US, so growing economies of Asia with the United States. And with just 6 fiber pairs, they're able to achieve 60 terabits per second of bandwidth, which is thousands of times, I believe, larger. Tera is way, way larger than mega. You can do the math there, but it's quite a bit bigger. So vast improvements even in fiber tech between 1988 and today, but not a lot of innovation in the material itself. So what is fiber? Basically, it's a piece of glass. It's a piece of glass that's made into a wire. It's a special glass. It's not just the kind of glass that you get, your bottles made out of or something, but it's basically still just glass. And what makes fiber incredible is that it has a property called total internal reflection. It's not actually total, but we call it total internal reflection. It means that almost none of the light that enters the cable will exit it except out the other side. So it doesn't bleed light at all. And if you've ever played with fiber, you might not have given this much thought, but if you shine a light on one end, it will come out the other with the same intensity. And the fiber itself isn't emitting any light. So if you're in the darkness and you shine your light on one end of the fiber will remain dark. You'll only see the light at the beginning and at the end, except for the light that's leaking out around kind of the sides from your light source. If you shine a perfect laser into the fiber, you won't see anything except the in and the out, and that's pretty amazing. In practice, a tiny bit of light really does escape, something like 0.1%, and so you do need repeaters every few miles to amplify the light signal again, because otherwise it will degrade over very long distances. But light travels very, very fast, 300,000 kilometers a second. That's the speed of light, right, roughly. And Earth is 40,000 kilometers all the way around the largest part of its circumference. Why did I have that? Anybody know why I cut that in half for my calculation here? When I'm talking about, basically I'm trying to figure out what's the worst case for communicating with another person on the planet using the speed of light. Why did I cut the circumference of the Earth in half? So if I take that 40 divided by 300, then I get 0.13 seconds, or 130 milliseconds. Is that supposed to be 20 divided by 300? Let's see. No, actually, 20 divided by 300 is half that still, so we're talking about 6-7 seconds. So the worst case halfway around the world is 6-7 seconds. And if someone mentioned in the YouTube chat, you're not going to go around the world to talk to somebody. The worst case is halfway around the world. If they were more than halfway around the world, it would be faster to go around the other way. Right? So in practice, that's not always possible, but the worst case should be, assuming that you have perfectly straight cables everywhere, halfway around the world. So 6 or 7 seconds is the best we'll ever be able to do. 6 or 7 milliseconds is the best we'll ever be able to do, according to our modern understanding of physics. You literally can't speak to someone on the other side of the world faster than that, which is disappointing because that's actually quite a bit of ping if you think about it, and it means that if we were ever to go into space, to Mars or something, the worst or the best that we could do to communicate with a place like Mars would be on the order of minutes because it's so far away. Even the moon takes minutes for light to get there and back. Steam, my old enemy. Always forget. Let's look at a relatively modern map of the fiber that connects the world. Looks a lot like the copper wire that once connected the world before. Only now you have a lot more cables between the United States and Asia. You got tons. So in addition to doing a ton of business with Europe, the United States now does a ton of business with Asia as well. And you even start getting connections to Africa and Australia, different places like that. there are still a lot of parts in the world you can see are very underserved. So if you live in Iceland or Greenland, you might have one fiber for your whole country connecting you. If you live in remote parts of Russia or those kinds of places, you might also not have too many undersea cables getting to you, but there are literally hundreds of cables under the sea today. So what threatens undersea fiber cables? What are the dangers beneath the sea? What can ruin your undersea fiber cables day? Someone said sharks. Sharks are a great danger beneath the sea. The sea itself, actually the sea is not that dangerous at the bottom. On the bottom not much happens. It pretty much just sits there and does nothing. The sea is very calm when you're 1,000 feet deep in it. Nothing happens down there. The only stuff that happens is that there's occasionally an earthquake or something, and a cable might get severed due to that, but it's incredibly rare. There's no currents, there's no waves, there's no storms. The bottom of the sea is really super quiet. So yeah, sharks. Sharks are a big danger. Hilariously, the first fiber lines laid down were plagued by shark attacks. It turns out that sharks hunt using fancy electromagnetic voodoo, and they like wires. It messes with their senses that they use to hunt, and so they think it's food and they bite it. And if they bite it, they break it. And so later cables, after the first couple, TAT8 and its successors, were made with heavier outer shielding, thick layers of metal or something in order to keep the fibers safe. Why was shark attack not so much a problem for the copper wire? Didn't get a lot of severed copper cables due to sharks. It still has electricity, so how come sharks didn't get bothered too much by copper? Alright, the other danger is idiots in fishing boats. Deep sea trawlers send a net out onto the bottom of the ocean to catch fish. You're not supposed to do that. It's bad for the environment, but a lot of people don't care because fish are worth money, and a lot of time they end up accidentally cutting undersea cables, which irritates everybody. So don't be a deep sea trawler and don't buy deep sea trawled fish. And then another problem is spies. Spies have been tapping undersea cables since the Cold War and probably before that. They sneak in there in their secret submarine and then they have to figure out a way to tap it. Tap usually means cut because it's very hard to tap into fiber without cutting it. Now you could allegedly tap into it in a number of different ways. There aren't a lot of confirming information out there about how they do it. But one way that you can see inside of a fiber cable is to bend it a little. You'll ruin the total internal reflection. But if you've degraded the signal, it's still possible for somebody to notice that you degraded the signal in that undersea cable. And that's not very good spying. So the art of getting into your undersea cable in secret is an art that all the nation states of the world engage in. And then also kicking other nation states out, so figuring out that someone else has tapped your cable and getting rid of them. Again, there are not that many undersea cables in the world. If you tap one, you get access to a ton of traffic between nations, and that's very valuable indeed. So nobody answered why sharks didn't eat copper wire as much. The simple answer is if they tried to chomp on a high voltage copper wire, they'd be dead before they managed to chew through it. So just by nature of its electricalness, it often was protected and didn't need quite as much shielding. The other answer is it's copper, so it's metal. It's a lot harder to chew through. What about on land? What do you do to lay fiber down on land? So fiber on land is a whole other issue. The ocean is pretty much fair game. Anybody can go down there and run some wires because nobody owns the ocean. Arr, a pirate is free. But land, not at all like that. Nation states have borders and their own political drama. If I want to run a cable from, let's say, England to Spain, well, if I go the ocean way, that's no problem. If I go the land way up to France, then I gotta figure out how to deal with the French and all that stuff. So that's no fun. Now I gotta go across all these different independent countries that probably don't want you to run their cable for free and might not like you and might cut it or might charge you rent and all that kind of stuff. And then also there's personal private property. You can't just run cable wherever you please in most of the free world, which means you can't run it in a straight line. And fiber's pretty bad at bending. Every time you bend, you need to put down some equipment. You actually have to make a turn. You have to bend it, put one end in the equipment, put the other end out the equipment, and that costs money because that equipment is expensive. And on land, there's all kinds of terrible things happening. There's storms and hurricanes and tsunamis and earthquakes and fires and hail and idiots in cars, and all of that stuff can lead to cut cables, which damages your fiber network and also makes it much more expensive to maintain it. But fiber is still the backbone of the LAN network. I'm not saying that fiber isn't what connects us on land, just that it costs a whole lot more to do so. But fiber is the dominant connection between all nations, cities. All large connections are still based on fiber lines. How do you share a fiber line then? This is a theme that's going to come up again on the physical layer. How do you split a fiber into multiple signals? So you want to be able to send more than just one pulse of light through the wire. One way to do it is time multiplexing. That's straightforward. In time multiplexing, everybody gets a turn to send their light. So everybody gets a time slot in which they get to send light. And when it's not your turn, you don't get to send light. And everyone has to sync up time slots at that point. You have to know whose turn it is to know who's talking. So time division multiplexing is fairly straightforward, but it also can be difficult to sync up those clocks so that you know whose turn it is. And it's also not particularly efficient. You're not really taking full advantage of your medium. The way that most fiber is split today is with wavelength or frequency multiplexing, using that same medium, the same fiber, to send different signals. So you can send pulses of light through fiber, and you can send pulses of different colors. So in the example picture there, some person is communicating on red, some person's communicating on green. If you're the one talking to green, then you would listen only for the green lights. If you're the one talking on blue, you would listen only for the blue lights. That allows you to use the same cable for lots of different communications at the same time. That new, faster cable from Google that we were talking about earlier uses 100 different wavelengths of light, so it can support 100 different conversations in one wire, 100 different transmissions in one wire. And we'll see multiplexing come up a lot in other physical layer applications, because multiplexing is kind of essential. If you have any kind of frequency band, if you're using any kind of medium, you want to optimize it to its maximum. You want to split it into as many different wavelengths or groups as possible so you can get the most out of your medium. Now, the hardest part of internet is the last mile, and some of you might have experience with this. Getting the internet to your home or business, the very end of the road, is tough. Fiber is the backbone between cities, even between communities. You probably have at least one fiber line running into your community, no matter where you live in the city. So there's probably a fiber line maybe at the end of your block, maybe at the end of your neighborhood, but somewhere in your neighborhood, somewhere within a few miles of you, there's probably a fiber line. And it gets to this question of why don't we just run that just a few more feet then to the house next door? Well, it turns out just going to that house next door is expensive, even if you live within just a few hundred feet of the fiber tap. Even if you're within eyesight of it, it can sometimes cost $10, $20, $50,000 to get it to your house, just because it's so expensive to run wire in urban areas. So one of the reasons that it's very hard is because the wires themselves are really hard to splice. It's hard to make connections. They're hard to work with. Fiber technicians make pretty good money, and they're pretty hard to come by already. It's hard to get permits to run new wires across the city. Nobody wants to see new wires. It's expensive to put down all the different equipment. Fiber requires a lot of equipment on top of the cabling, different repeaters and modems. They are pricey. Somebody asked if I had fiber in the YouTube chat, and I did at my old house. We'll get into that for a minute there. I think it might be the next slide or a few later. And then no one wants to run new cabling. There's a big aversion, at least in America, to running any kind of new cabling. Most of the wires on the poles outside are are the same that they've been since 1970. So Cleveland, the city where we reside, has fiber to the home in many areas, served primarily by AT&T. AT&T had an agreement to service so many homes with high-speed bandwidth, at least 100 megabits, which is what fiber is. And to fulfill that obligation as easily as possible, they targeted the highest density parts of Cleveland that they thought could afford fiber. So they targeted neighborhoods that had a reasonable amount of money, but also where the houses are really close together. So you'll find that most of the let's call them the lower middle class areas, the core suburbs of Cleveland, have the most fiber access. So places like where John Carroll's at might have fiber access because all the houses are really close together. I'm not actually sure if they have it there, but that would be the kind of place that'd be a good candidate. And where I used to live in South Euclid had it because the houses are very close together. And again, people have to be able to make enough money to afford fiber, which is not that expensive. They were charging between $60 and $100 a month for fiber when I was in that area. But beyond that, they don't care if you're extremely wealthy. So actually the wealthiest areas of Cleveland tend to not have fiber access because why would you? Why would you bother running fiber all the way out to the wealthy areas? Because the wealthiest areas in Cleveland are places where the houses are very far apart and generally have large yards, and that means longer runs, and that means more people who are annoying about their property rights and about having cables in their area and all of that stuff. In my neighborhood, all cable must be buried, which adds another expense. So they tend not to run fiber to those places. We'll probably never get fiber in this area just because it's so expensive. Just for fun, I did have it quoted out in this neighborhood when I moved here. The quote was somewhere around, I think it was $140,000 to get it installed, which is actually more than the price of the house I moved out of. So if you think about it, the fiber line that I had at my old house was worth more than the house, if you think about it just in terms of its fair market value. But that's not how it works because fiber was expanded primarily through government grants and that sort of thing, and the price that they offer it at doesn't necessarily reflect cost, but nonetheless a gigabyte connection to your home is probably worth, at least to somebody, it costs somebody over $100,000 probably per home to get it to you. That's not an unusual estimate in a city. It might be cheaper in the country where you can run cable cheaper, but the costs per mile in the city are very expensive, at least in the tens of thousands. So if you have access to fiber where you live, get it. Don't get cable, don't get DSL, get fiber. It's definitely the best internet. Fiber to the home cannot be matched. So other last mile techs are dial-up, which runs through your phone line, DSL, cable, and modem, mobile connections. Those are your other options in last mile. Dial-up and early DSL connections use phone lines, electrical signal. Notice I'm not describing what DSL stands for. I don't think it matters because no one ever refers to it as anything but DSL. The actual definition of the acronym is irrelevant. I don't even remember what it stands for. Dial-up and early DSL use phone lines, electrical signals. Those are again sent over copper, and again they have low bandwidth, and a lot of that is due to physics. Electricity propagates slowly through a copper cable, not anywhere near the speed of light. It's significantly slower, and there's limits on how fast you can change your pulses of electricity. When you buy DSL, you're buying a dedicated socket. That bandwidth is basically always yours. So if you buy 1.5 megabits a second, you're getting 1.5 megabits a second always, even when you're not using it. That's very inefficient. It's nice to be able to sell capacity on the basis that the person's not, it's available, but if everybody doesn't use it at the same time, you're able to oversell. So if your line can support 100 megabits and you know that in a given neighborhood only 30% of people will be online at any given time, you can actually sell 300 megabits worth of bandwidth and just hope that they all don't get on at the same time. That's standard practice in other mediums, but for DSL, you buy the socket, you get the socket. That's actually not great for how much it costs you and how much bandwidth you can get. And signal loss over copper is bad. If you are one of the homes that's far away from the head, from where the DSL signal starts, you're going to get terrible performance and terrible internet. There's a lot of loss of signal due to electrical interference, and since that cable tends to hang on electrical lines, there's electrical interference all over the place. So not exactly a great medium. The only pro to DSL is it's usually pretty consistent. If you have a good connection to the head, so if you're relatively close, it's going to be consistently good. You're going to get low bandwidth, but consistently it's not going to cut out too often, and you're not going to get big changes in latency. Of course, if you're in the far away part, you're far from the head, then it's going to be consistently crappy, and it's really never going to get better. But in other parts of the world, and to an extent in America, they don't see that much of it. They continue to improve on DSL and using various tricks, using multiplexing, using physics tricks like twisting the wires into pairs to cut down interference. They managed to pump up DSL until they got to VDSL, which is basically the last stage of DSL technology. It caps out at 100 megabits a second, so a tenth of gigabit fiber. It's still copper wire, but not a terrible speed. 100 is very respectable, more than enough for most people using the internet. So why is the US primarily based on cable? Almost everybody has cable internet in America, or at least access to cable internet in America. Why is America so obsessed with cable internet? This is more true of the USA than anywhere else, pretty much. Europe also has a lot of cable internet, but not as much as us. They tended to invest more into DSL. And then why is South Korea's internet so good? In South Korea, almost everybody has fiber to the home, and they have it for very little money. They have it for $30 a month equivalent, something like that. So somebody answered on live, because we're gamers and we need internet no matter where we are. Well, if that was true, then wouldn't we have invested in sick fiber instead of having cable? Why do we all have cable? If we were real gamers, we'd get the best. We'd get fiber. Okay, so the answer is that the US was already heavily invested in cable. Someone answered that South Korea needs the best of the best for their esports. No, esports in South Korea grew because South Korea has the best internet in the world. You really can't be an esports competitor on cable internet. The variations in latency on cable and DSL and the pings that you get are too crappy for you to be a professional. The latency that you get on fiber is incredibly consistent, which is what you need for gaming. You need an incredibly consistent latency, and it's also incredibly low compared to all the other technologies. So that's one of those examples of putting the horse before the cart. It's actually, they have that huge esports scene because they had the great internet. And another reason that many people advocate for improving the United States internet infrastructure, because good internet grows industry in ways you would not expect. I don't think anybody 30 years ago would have expected an esports scene to exist at all. But why does South Korea have fiber everywhere? Let's go back to that. So if anyone can answer that. Why do they have fiber everywhere instead of DSL or cable? But okay, back to the US. The US was already invested in cable by the 60s. They had decided that everybody in the United States should have access to cable television, and they made it happen. They spent a tremendous amount of money on cable all over the place. Somebody asked what my internet speed is. I'm now paying significantly more than I paid for fiber to get 400 down and just 20, I believe, up. Whereas on fiber I had gigabit, which is 1,000 megabits down and 1,000 up. All right, so I've cut my upload by 50 and my download in half, and I'm still paying more, and I have worse latency. So there's a post on YouTube Live about the private lines ran around the globe to get the fastest stock market trading. That's true, but if you want the fastest trading, you have to live near the stock exchange, because the fastest you can do across the ocean, remember, because of the speed of light, is a few milliseconds. So yeah, people compete to get to the fastest in the stock exchange. People will actually, in New York, purchase a line of sight communication to the New York Stock Exchange, which transmits over the air and is just slightly faster than fiber to save a few microseconds. So the US was already invested heavily in cable. They decided to piggyback on it for internet. That's the only reason that the US primarily has cable in it, because the cable were already there. The cables were already run by the time the internet became a thing, so they just decided, well, we'll use these cables we already had, we'll figure out a way to make it work, whatever. And that's what they did. So originally, cable television channels, there was this big frequency range. Most of it was TV, part of it was for FM radio. And each television channel was 6 megahertz big. There was something like 100 standard channels. And so they allocated about 600 megahertz of band. Every time you changed the channel, you actually moved up to the next 6 megahertz block. Okay, and so what cable companies actually sell you when they sell you bandwidth is some piece of that remaining block, the channels that weren't allocated. And these days, some of those TV channels have been compressed, so they actually have more bandwidth for sale that's not being used for TV anymore. And if they ever decide to completely discontinue cable television, they'll have even more bandwidth that they can sell you. Now, what about the upload? That's going to be tough, right? Because cable was not designed to receive data. Cable was just designed to send you TV. There was this little teeny-weeny band in the beginning of the cable spectrum that was used kind of just in case TVs ever needed to talk back to the network. It was not intended to be used as much as it's used today, not even close. And that band is what we use for all of our upload. And I'm going to go back to the previous slide for a second. This teeny weeny little band at the beginning, just something like 40 megahertz big, is all the upload that's available on your cable line, which is why when you purchase cable, you get much more download than you get upload. There's also limited units available. There's only so many channels. If you want to serve more homes, then you need to build another head end, another point at which the connections are split. So your cable connection is shared by neighborhood or by a block of homes. If they want to build more bandwidth into the infrastructure, they have to build another head end. That takes equipment and money. And one of the things you'll notice is that we all get the same channels at the same time, right? Cable transmits to everybody at once. So everybody is sharing the same signal. Everybody's getting the same channels and everything at the same time. That means you're also all getting your internet communication at the same time together. You're all actually talking into the same wire, the wire that's used for television. You're all getting information on the same wire. You're just extracting the portion that was meant for you, so the channel that you're tuned into. But all the other channels, everybody else's internet, is in that same wire somewhere. You can just pull it right out. It also means that if you want to mess with a neighborhood, if you want to kill the cable for your entire street, all you have to do is plug any electrical interference into your coaxial cable, and you will kill the internet to the entire street, because you all share the cable. And that's why cable is so unreliable and cuts out all the time, because idiots go to the curb, pick up their CRT television that they found in the trash and try to plug it in and upload crapload of interference into the coax and then damage the internet for the whole neighborhood, which is very, very difficult for them to hunt down and figure out. Or any number of other reasons why there might be interference in the coaxial cable. And it's also obviously really vulnerable to vandals or bandits or people who just want to be mean. You could shut down the cable internet to a block really without even trying. Another problem with cable and DSL and dial-up is that they're not digital. Fiber is already basically digital. You have zeros and ones baked in. The light being on a little is a 0, the light being on a lot is a 1. That's one scheme you could use. Now you just have to sync up timings to read zeros and ones. So how long does the light need to be on or off for me to count that as a 1 or a 0? Copper cable and, cable is also copper. Coaxial lines are copper. So all the copper cable systems are not digital. Voltages change slowly. They don't change instantly like light does, because electricity propagates slowly through copper. So you end up with a signal that looks more like a sinusoid. How do you get digital data out of a sinusoid? So you have to learn how to do this complicated math, the analog to digital conversion. And the most important tech here is QAM, quadrature amplitude modulation. QAM allows you to take a sinusoid and take some info about that sinusoid and turn it into digital bits. And QAM is where all of the innovation in cable's been happening. So someone mentioned DOCSIS 3.1 in the YouTube live chat. DOCSIS innovations have mostly been upgrades to QAM, figuring out how to pack more and more bits into a sinusoid of the same length. This is mostly advanced maths, engineering, and physics stuff that's not particularly important to you, but it's important to consider that the actual cables haven't gotten any better than they were in 1980. We've just gotten better at packing information into those cables. And now, because we've gotten so good at it, you can actually get fiber-like download speeds. You can get gigabit cable download speeds, primarily due to improvements in QAM. But again, that's only down. Cable can't compete for upload just because there's not enough upload to sell, no matter how good they get at QAM. And this is probably it for QAM. There might be one more generation of improvement beyond DOCSIS 3, but it won't be a big improvement. So this is probably the terminal technology for cable. So the future of the last mile, hopefully, because nobody wants to run new cable in any political climate, in places like the United States with too much private property, there's no way for you to run cable reasonably through a neighborhood for anything resembling what it would be worth. You know, all the houses would have to pay hundreds of dollars a month to make it worth it. No one's going to pay that, so it's probably never going to be worth it. So the future of the last mile in most of the Western world is probably going to be wireless. And that's great because light travels even faster through air than it does through glass. Glass slows down light a little bit. You're actually not getting the full 300,000 kilometers a second through glass. 4G is already pretty decent. 4G competes with DSL and low-end cable, older cable tech on speed. But the latency to the tower is pretty poor. You're getting 50 milliseconds. You could have gone around the world 8 times, or halfway around the world 8 times, or around the world 4 times in the time it took you to send that message just to the cell tower, right? And the further the cell tower away is, the worse it is. So depending on how far you are from the cell tower, it could be even worse. But 5G, 5th generation wireless technology, which doesn't cause pandemics, should have fiber-like speeds and still doesn't require cable. The latency could be under 5 milliseconds for 5G. This is because of just improvements to the frequencies that they're allowed to use and all kinds of other physics magic. But unfortunately, because of the pandemic, 5G manufacturing has been pretty much decimated. It's very hard to get 5G equipment, and so the rollout of 5G has been pushed back probably a couple of years by the pandemic. Fiber will still connect 5G towers together, and then the 5G towers will just serve the last mile. That'll probably be the future of internet connection. This has already been deployed in places like South Korea. Nobody answered the question of why South Korea has fiber and the US doesn't. The question has 2 answers. Number one, South Korea is small, so running the fiber was cheap, because it's, unlike the United States, not massive. All the cities are pretty close together. Everybody lives pretty close together. There's not that much to run. And number 2, more important, South Korea modernized last. So they modernized after the Korean War. They didn't already have cable, which means they had to run something new. And fiber was the fanciest and newest tech, so why would you run anything else? They happened to run the best tech that they had available at the time, whereas the US had already run the best tech available at the time 20 years ago and was stuck with it by virtue of having already done it. So the later you are to modernize, sometimes the better things work out. What are the biggest downsides of wireless communication? Well, wireless communication depends a lot on QAM, which depends on your ability to accurately read a sinusoid, which depends on it being transmitted very reliably. And that means that if it's raining, you lose a lot of your bandwidth. So the future might be a future where when it rains, we can't go on the internet, which is a huge disadvantage, because when do people like to go on the internet? When it rains, right? 5G mitigates this to an extent by the bands that they use. They're a little bit better at penetrating through rain and whatever, but still not perfect. So why does this matter to you as a developer? Well, number one, remember that most of your users rely on cable or DSL, but primarily cable in the US, and they have very limited upload. So while they can receive data from you pretty quickly, they can't give it to you very quickly. So a lot of your applications are going to be imbalanced in the sense that you send much more than you receive. Your users have a variety of technologies with varied speeds and latency. You can't count on your users to have a consistent connection. You can't even count on everybody to have the same latency or the same internet speed. There's all kinds of different ones out there. Also got to think about the fact that everything you make depends on an extremely complicated global network of cables, and that network of cables can often die. Somebody can cut a fiber cable with a deep sea trawler, and while the internet will route around any kind of damage very quickly, your traffic can briefly die as well. It's actually possible for your traffic to die long term too, especially if you live in a region without too many fiber connections. So we might talk about this again later, but the entire nation of, I think, Romania got cut off from the internet for a whole day because somebody accidentally dug up a fiber cable and cut it. So those are examples of the whole internet going out just because of one physical layer mistake. So all of that tech that we just talked about, all that technology, just gets the internet to your modem. So those are the techs that are used by your service provider to transmit your signals between cities, countries, neighborhoods, and then from the head end to your house. So once it's in your house, it gets to your modem, and then the modem translates it into one of the following two technologies. These are the technologies that most internet connected devices use. So all of the stuff that's connected in your house, all of the stuff that's connected at your work, is using either Ethernet, which are twisted pair copper wires, or Wi-Fi, which is a microwave. Okay, so the modem gets your DSL, your cable, your fiber, whatever. After that, your modem turns it into Ethernet, Wi-Fi, etc. You'll see on the back of your modem there's going to be a connection to either the fiber, the coaxial cable, the phone line, and then coming out of your modem will be a bunch of Ethernet ports, or maybe a Wi-Fi signal if you have a modem that's also a wireless router. Let's talk first about Ethernet. We might not get through this, but we'll just start it out. Generations of Ethernet are dubbed CAT, so Cat5e is the most common today. You'll see most places are wired for Cat5e. Cat5e supports up to a gigabit, and since most people don't have more than that, in fact almost nobody has more than that, the adoption of Cat6 has been very slow, also because Cat6 is almost 40% more expensive. 5e, 1,000 feet of 5e in Cleveland today, it's about $70. 1,000 feet of 6 is $100. And then if you want Teflon jacket, which you need to do if you're running the cable through HVAC, so if you're running it alongside heating or cooling, then you need to get the Teflon jacket, which is roughly doubling the cost. And then you can also get thicker insulation, which doubles the cost again, but only huge ballers get the thick insulation. So most places just buy regular old Cat5e because gigabit internet is more than good enough for pretty much everybody. Somebody mentioned that Cat6 is a pain to terminate as well, so I'm going to skip to this slide for a second and show you the glorious Ethernet plug. Most of you are used to having this on the end of your cables. You're used to having your beautiful Ethernet jack, your RJ45, which hasn't changed shape in a very, very long time and is indeed a bloody pain to terminate. So if you go back to what the wire looks like, you'll notice it's a bunch of differently colored wires. Each of those has to go in a very specific hole and be paired with another very specific wire, and they need to clip them all together. So it's a big pain. They sell little plastic tools for it, but it's not something that most people do themselves, and it's not very fun to do at all. Why are they twisted? So imagine that there's some radiation coming from over here, and you've run the two wires in parallel. In that case, the red wire, which is closer to the radiation that's coming in, will get more of whatever the radiation is. So if it's raising the voltage, then it's going to get raised more than the blue one. So the red one has more interference than the blue one because the blue one's further away. Now you have a problem. If they're twisted, then each of them gets the increased interference only half the time, which means they have the same amount of interference, and it actually cancels out. So this allows you to send signals much further than if they weren't twisted, and it actually allows you to get up to 300 feet. Sometimes it's possible to exceed that a little bit if they're very straight, but 300 feet is pretty much the max between any two receivers. So if you go more than 300 feet, you have to put a switch or something, and then you can keep running. So the switch acts as a repeater to boost the signal and then start it up again. And then RJ45 once more. And then next time we will finish talking about Wi-Fi and start on the next layer up. All right, everybody, that's it for today. Enjoy your Monday off. Hopefully you were actually supposed to get it, and I'm not just misreading the calendar. See you guys Wednesday.